I think we may as well get started if you're happy enough with that, Tim.
Sure.
Thank you. I should say it's a pleasure. I think I'm assuming that almost everyone on this call must know who Tim Guriev is. Just for those who don't, Tim is a mathematical physicist, got his PhD in Leningrad State University, and he's currently a principal research fellow at the University of Melbourne, an honorary senior research fellow at the University of Sydney, an adjunct senior research fellow at Monash University, and an adjunct professor at the University of New England. And his research, as most of you will know, is focused on theoretical and computation aspects of new techniques for X-ray imaging, computed tomography, and electron microscopy. And I have to say that I've been working with Tim now, it must be the best part of a decade. And I have yet to come across, over my 3 decades of working in university, or even more than that, such a humble and yet such an effective researcher. So I'm really pleased when Tim walked through my door around 10 years ago and suggested some collaboration around PCT and seeing how we could move to the clinical environment. And it's been a wonderful collaboration since. So with no further ado, Tim, I'll hand it over to you. And Tim's going to talk about a unified fast reconstruction algorithm for conventional phase contrast and diffraction tomography. Thanks, Tim.
Thank you very much for the very kind words, Patrick. I'll try to share my screen now. How does this look?
Perfect. Thank you.
Excellent. All right. So as Patrick said, I will be talking today about a new CT reconstruction algorithm that we have developed over the course of the last year or so. And my talk, of course, will be in the context of our ongoing phase contrast breast CT project at the Imaging and Medical Beamline at the Australian Synchrotron, where we have scanned now over 120 mastectomies over the course of 6-7 years. Okay. And when we scan mastectomies, we usually receive them from the Eastern Health, our colleagues, for which we are, of course, very grateful for the supply of these samples. Then we place a sample into a plastic container, put it on the rotating stage. Can you see my my pointer?
We do, yeah.
Okay.
Yes, we can.
So
Yeah.
we place the sample in the plastic container, put it on the rotating stage, irradiate it, collect many images at different rotational position, and then reconstruct the 3-dimensional distribution of the internal structure of the object using a combination of the homogeneous transport of intensity equation phase retrieval algorithm and the filtered back projection computer tomography reconstruction algorithm as implemented in our proprietary software extract and its different versions. And I have to say that these 2 3-dimensional renderings were produced by Sherry Mayer from, I think, the very first 2 mastectomies that we collected at IMBL. So my talk is about this image reconstruction stage, where we go from the collected projection images to the 3-dimensional representation of a mastectomy or another object. And in order to explain this work, I have to temporarily go to the fundamentals of the X-ray physics and remind the audience that we see objects usually effectively by throwing photons at them and observing the result of the interactions of those photons with the object. And the interaction channels, the most frequent interaction channels are absorption, reflection, and refraction. And by the way, of course, it can be not just photons, it can be electrons or other particles used in imaging, but we use X-ray photons in this work. So in the case of X-ray imaging, for 100 years until quite recently, only absorption contrast was utilized, and that is unfortunately can be damaging to the human tissue and can even induce secondary cancer. Therefore, the reduction of the radiation dose is the main goal, one of the main goals of our project. So as I said, the 100 years of X-ray imaging, they actually started in 1895 when William Röntgen discovered X-rays. And his images were, of course, based on differential absorption of X-rays in human body parts or in different objects that he imaged. And then 100 years later, in 1995, the phase contrast imaging with X-rays has been demonstrated, and it showed a better contrast, especially for soft tissues, as shown here, compared to absorption contrast at the same dose. So as for the mechanisms of the amplitude and phase contrast, then absorption contrast, as I think I mentioned already, is based on differential absorption of incident X-rays in different parts of an imaged object. And as a result, we get the contrast, usually black and white contrast in the registered image, where we get fewer photons in the areas where the absorption was stronger, or more photons where the absorption was weaker. The refraction contrast is based not on the absorption, but on the deviation of the trajectory of X-rays upon their interaction with the object. And that refraction is usually the strongest at the edges and interfaces in the object. Therefore, the edges get somewhat emphasized in the images. But in order to see that emphasis or the phase contrast, we usually need to allow the image to propagate over some distance. And then after that free space propagation of the transmitted wave, the phase contrast can be observed in the variation of the intensity in the image. Quite often, we want to reconstruct not just the projected density of an object, which one could usually get directly from the absorption or phase contrast image, but we want to reconstruct the whole three-dimensional distribution of a particular property in the object. In the case of X-ray imaging, that property is the refractive index. So we can reconstruct the three-dimensional distribution of the refractive index inside the object on the basis of multiple propagated images that we collect at some distance from the object using a position-sensitive detector. So in that process, the object can be rotated in 3 dimensions. In our conventional CT scans, we usually rotate the object only around one axis, which is typically that y-axis, which is orthogonal to the direction of propagation of the plane incident wave. But in principle, the object can be rotated over all 3 axes in 3D in an arbitrary way, and I will show that my new algorithm can easily cover an arbitrary scanning geometry, arbitrary rotation. At that point, I would like to mention an exciting possibility for reconstructing the 3-dimensional structure, not from multiple images, but just from a single image, if certain conditions are met. And that type of 3-dimensional imaging is sometimes called virtual optical sectioning. And in principle, the method that I'm going to describe allows for such virtual optical sectioning, but there is, as I said, there are certain conditions that need to be satisfied for that to be possible. And more routinely, of course, the object still needs to be rotated, and multiple images need to be collected in order for the refractive index in 3D to be reconstructed by tomographic means. So going deeper into the X-ray interaction physics, I would like to mention that there are three basic models which are typically used for describing the propagation of X-rays through the object and interaction of X-rays with the internal structure of an object. The most complete, the most general model is what's sometimes called multi-slice model. It splits the object into virtual thin slices orthogonal to the direction of incident X-rays. And in each slice, both the propagation of X-rays through the matter and the interaction of X-rays with the scattering center is accounted for. And that is done then repeatedly. So as a result, the so-called multiple scattering of X-rays, where an X-ray can scatter from one inclusion in the object and then go to another inclusion and be scattered there, and so that it can happen multiple times in principle. And all these multiple scattering processes, as well as the Fresnel diffraction of X-rays inside the object, are taken into account in this general model. In a simplified model that we currently use in our work, one adopts a so-called projection approximation for the description of propagation of X-rays through the object. And in this approximation, which actually works quite well for hard X-rays and soft matter, the trajectories of X-rays through the object are considered to be straight. So any deviation due to scattering from the straight trajectories is neglected because it's really small. And then after the propagation, the free space propagation through the object, the free space propagation of the transmitted wave from the exit surface to the detector is calculated using Fresnel diffraction integrals. But the Fresnel diffraction inside the object is not taken into account. Another way to simplify the problem is to use this so-called firstborn or the weak diffraction model, which is actually the basis for the new method, which I'm going to describe today. And in this model, the Fresnel diffraction inside the object is taken into account, but any scattering is allowed to happen only once for a given X-ray. So if an X-ray is scattered on a certain inclusion in the object, then we assume that it then propagates from that point of interaction to the detector without any further interaction with the object. And so we apply that for every incident X-ray. As you can see from that picture, hopefully, the deviation of X-rays from the straight trajectories are incorporated into this model. But as I said, multiple scattering is not. So that's the third model. And by the way, just to repeat, in all these three models, the free space propagation between the exit surface of the sample and the detector are accounted for using the same Fresnel diffraction model. So with each of these three forward propagation models, a solution of the corresponding inverse imaging problem is associated. By the way, I'm ignoring the fact that, to simplify the description, I'm currently ignoring the fact that the object is rotated during the scan. So I'm just considering a single image for simplicity, but please keep in mind that in principle, this whole process needs to be repeated for every rotational position of the object and for every transmitted image. So the inverse problem corresponding to the full multi-slice approach consists of the repeated forward propagation using this multi-slice model, which is done numerically, followed by the free space propagation, and then the resultant calculated image is compared with the experimental image. And generally, the difference between the two is minimized using some global functional approach, which I'm, of course, not going to go into the details, but it's sort of an iterative process, which are known to be pretty complicated computationally, and usually the existence or the uniqueness of the solution or its stability cannot be guaranteed. So it's quite challenging in terms of the numerical implementation. In the projection approximation model that we currently use, we first apply the, I will be using this slang TIE home because I don't want to repeat the words homogeneous transport of intensity equation every time, so please excuse my language. But we use this TIE home phase retrieval for each image, which allows us to effectively backpropagate the image from the detector to the exit plane of the sample. And then we use the conventional computed tomography, filtered back projection approach to reconstruct the distribution of the refractive index based on the projection approximation. In the new method, the approach is different. Excuse me. We apply the phase retrieval, but a phase retrieval here can be different from the TIE home method, and I will describe it in a minute. But after we apply phase retrieval and reconstruct the complex wave at the detector plane, we backpropagate it directly to multiple planes inside the object. So we don't go to the exit surface following by the conventional CT reconstruction. We go directly inside the sample. So in the sense, we combine the phase retrieval and the backpropagation into a single process in this new method. And there are some key parameters in this business, in the three-dimensional imaging, parameters such as contrast, spatial resolution, and the more esoteric things, which I need to describe today. These things are called, for example, depth of field or depth of focus, and the so-called evil sphere curvature, which are all related to each other. And I'll try to briefly describe it now. So the depth of field is actually related to the degree of the deviation of the scattered photons from the straight trajectory. So if k naught is the incident direction and kh is the scattered direction, and if that angle becomes large, one would say that the depth of field becomes smaller. So that sort of a uniform field which you find around the object becomes more constrained around the sample because it starts to expand very soon after the interaction. So and the dual process is called the depth of focus. When you use not the plane incident wave, but the, say, convergent or the divergent incident wave, then there is a thing called depth of focus, which is utilized quite effectively in visual light microscopy, say in confocal microscopy, which allows sometimes an experimenter to limit the effective imaging plane to a certain transverse area section of the sample. So you kind of optically sectioning the sample, and that's, if you see the point, it's a bit of an alternative to tomography, because as I was trying to hint before, with the certain conditions met, when the depth of focus or depth of field is small, it's becoming to be possible to reconstruct the three-dimensional structure from a single two-dimensional image by means of that reversal of that process, where you can sort of reverse focus onto different planes inside the object numerically. And I'll show you an example shortly. So that's why these things, depths of focus and depths of field, are so important. In our usual press CT imaging, the depth of field is very large in the sense that it's much larger than the sample thickness. And so that deviation angle is negligible compared well, say the deviation of X-rays during their propagation inside the object is negligible compared to the thickness of the sample. And therefore, we can use this straight rate model successfully, right? And one can also say that that evil sphere curvature, which is actually the surface circumscribed by these scattered vectors, that evil sphere becomes pretty flat because that angle is small. Oops, sorry. So the evil sphere is flat, the depth of field is large, and that's the typical regime of our work. But I want to investigate different options today because some of them are potentially quite interesting. So just continuing from what I was saying before, in the process of the three-dimensional reconstruction of the object, we effectively backpropagate the complex amplitudes from the image planes inside the object. We do it for different images, different imaging planes. And in the method that I'm going to describe today, the object is effectively represented as a collection of independent scattering centers, or if you like, incoherently scattering centers. And that's, of course, a big simplification, but it seems to be working fine. Excuse me. So again, the object can be reconstructed sometimes from a single image, which is called for virtual optical sectioning, or from multiple images in the case of conventional or diffraction tomography. DT stands for diffraction tomography. And by the way, I'm using the words defocused images and propagated images interchangeably. That means the same thing, the images which are collected at some distance from the sample. So the reconstruction, which requires this backpropagation, of course, includes the phase retrieval problem, again, which I already mentioned. But let me just go back to it again in a slightly more general context and say that the phase retrieval consists of the reconstruction of the object phase from the registered intensity. And in the method that I'm describing today, that phase retrieval is done basically according to what is sometimes called the method of contrast transfer function correction. So you can see that the phase is reconstructed from the intensity by means of the Fourier space division by a function, which is this simplified case of pure phase object. It's the sine function. So this is the contrast transfer function, which is required in order to get a phase from the registered image. Just an aside note, as my colleague David Paganin noticed at some stage, we are not really interested in the phase retrieval as such. We are interested in reconstructing actually the complex wave such that on its backpropagation, it can give us a good indication of the internal structure of the sample. And that is, although it's related to phase retrieval, that's not necessarily the same thing. And there are methods which we have investigated where we actually substitute a different phase, which is not the real phase of the scattered wave, but something else. And that also can be done, although I'm not going to discuss it further today. Just at the side that this phase retrieval is not the only way to approach this problem. Okay, and what we noticed is that in the process of that backpropagation, the backpropagated wave with the retrieved phase or another properly selected phase tends to produce a peak at the position of strong scattering centers inside the object, which can be atoms in the case of electron imaging, or can be, say, microcalcifications in the case of breast imaging or something else. The thing is that the width of that peak is proportional to the depth of field. So that's effectively what one can call the longitudinal resolution of the method. If that resolution is high, the peak is narrow, one can do, again, this virtual optical sectioning thing. But in our current conditions, that the depth of field, as I said, is very large. Therefore, the peak is actually pretty much absent. We have the flat profile on the back propagation. So from a single image, we cannot say where the scattering centers, where the structure sits along the ray. It sits somewhere inside the sample. We have this transverse resolution, which is shown in our two-dimensional image, but we don't have the depth resolution as such. And we get this three-dimensional resolution only after combining multiple images, collected from different illumination direction. When we combine them, we get these backpropagated rays intersecting and producing the distribution of the refractive index at the right spots. So we get the peaks at the right spots in 3D only after we do this reconstruction from multiple images, right? But when the depth of field is small, the peaks are high, one can do this virtual optical sectioning. And this is an example in the context of electron microscopy, but I'll try to mention that it may become relevant to X-ray imaging under certain circumstances. But just look at that. I think it's interesting in itself. So we are imaging a molecule here. That's a single two-dimensional image. And that's a three-dimensional reconstruction using the method that I'm about to describe in detail. The three-dimensional reconstruction from a single image. And that's a slice from that reconstruction where this Z longitudinal direction is the direction from the source to the sample. And you see where atoms are, we get these elongated peaks. So we get some indication of the longitudinal, so along Z position of each atom. And if we just locate the peaks of these blobs, we can find quite accurately the location of every single atom in this molecule from a single two-dimensional image. So that's the virtual optical sectioning. Would be great, of course, to do it with X-rays because we would need only a single image to reconstruct the whole three-dimensional object, but it's challenging. More generally, the method which I'm describing today, which is called unified tomographic reconstruction. Unified because it covers diffraction tomography, phase tomography, and conventional tomography in a single method, single reconstruction formula. So, physically, in this method, as I already at least partially described, what we do, we take this all available images, and for each one of them, we reconstruct the phase and backpropagate it, and that effectively gives us the distribution of this refractive index that we are trying to get on a so-called evil sphere, and those are these blue caps shown here. In each case, for each image, that cap is orthogonal to the propagation direction. So when we have multiple directions, we have these multiple caps. And the goal is to have so many images that those caps will sweep the whole three-dimensional volume. And then we will be able to reconstruct the whole sample, right? So each image contributes to this, just a cap, but multiple images can produce the whole sphere with an Fourier transform, the three-dimensional Fourier transform of that distribution inside that sphere, and that gives us the spatial distribution of the refractive index in this method. And now I have to apologize because I'll have two slides with mathematics. I'm sorry for that, but really these two slides are the gist of my talk. They describe the method as opposed to what I was saying previously. It was mainly an introduction, and to what I will be saying after these two slides, it will be consequences or the examples of the application of the method. But as far as the method itself is concerned, it's here. So I'll try to explain it. Please ignore the secondary details. But I will try to argue that what happens in this formula is precisely what happens in this picture, right? So we have these incident images, which we flat field correct as usual, as we do now. We correct them for the incident illumination. We Fourier transform them, each image. We apply this a little bit complicated contrast transfer function, and that gives us the Fourier coefficients of our refractive index that we are trying to find, right? And we do it for every image, and every image gives the contribution to certain coefficients. And in that sense, there's another last important quantity, which is denoted as n with the subindex q orthogonal. This is basically the sampling filter that counts every fractional contribution of a given image to a given Fourier coefficient in the refractive index. So we count this contribution, and in the end, we divide by the number of this contribution. And that actually corresponds in our current method to the so-called ramp filter. So the ramp filter, in the case of the scanning around a single axis, appears in this new method automatically by means of these weighting coefficients. But this is completely flexible. You can have any arbitrary scanning geometry, and the corresponding sampling filter will be created automatically in the process of reconstruction. So again, the whole process is very straightforward. We just take the image, calculate its contribution to the result we are trying to get, and go to the next image, etc., counting these contributions, and then dividing by them in the end. So my second and last mathematical slide just shows that this general formula, which I showed here, sorry, I'm getting worse and worse in the sense of my voice, but I have to apologize. So that general formula reduces to the known reconstruction formulas in the corresponding cases. For example, in the case of conventional diffraction CT, when one can ignore the evil sphere curvature, that second term with the cosine disappears. It disappears because I don't want to go too much into details, but it disappears because the images at opposite directions become symmetrical, and these terms cancel each other for the two opposite directions. So we left with that sine function, and that's a conventional phase contrast transfer function of the diffraction CT, as used, for example, currently in the electron cryomicroscopy. Right? Okay. So if the propagation distance becomes smaller, one can approximate the sign in this contrast transfer function by its argument. And that gives us the transport of intensity phase retrieval method that we are using now. So we just replace sign by its argument, and here you are with the very tiny notational difference that my sigma here is not our usual delta to beta, but it's minus beta to delta. But otherwise, it's exactly the transport of intensity equation that is implemented in extract and that we use for our tomographic phase contrast tomography. Finally, when this propagation distance becomes really small, it can be substituted, excuse me, replaced by 0. So you put 0 here. What you get is the Fourier slide theorem of conventional absorption-based CT. So that means that this general formula that I presented here, under the right circumstances, it automatically converts into the conventional phase contrast or diffraction tomography, and it incorporates all of them in one formula. And this new method has a number of certain advantages. So the first one I already explained. The second one is that it can, in general, can take the evil sphere curvature into account. It can also be applied in arbitrary scanning geometry. We are no longer limited to scanning the object around a single axis. I think there potentially can be advantages into modifying the scan and doing some sort of a rotation around other axes as much as possible. I think it can give us more information at a lower dose, but this method can immediately accommodate any such imaging geometry, just as is. And by the way, the propagation distances for different images can be different. It doesn't matter. And overall, this new method can cope with the incomplete data quite well, except that, of course, you cannot defeat the sampling requirements. You still need to probe, excuse me, to probe every part of the object in order to be able to reconstruct its refractive properties in 3D. And finally, and that will be demonstrated in a minute, this new method can easily incorporate three-dimensional noise filtering. And one can use the knowledge about the noise behavior in input images in that process. So just one quick example from the electron microscopy before I move to the more relevant X-ray imaging examples. But this one demonstrates that the new method can effectively account for the evil sphere curvature for the short depth of field in nanoparticle imaging. So this is the reconstruction using new method, which shows all the atoms very nicely. And this is the method which does exactly the same, but without the evil sphere curvature. So the more conventional method. And you see how the atom becomes progressively blurred towards the periphery, which is further and further from the center of rotation. That's the effect of the evil sphere, which when it's not taken into account. Excuse me. So now to our mastectomy samples. And here's one of the three examples that I'm going to show. So that's one of our typical scans at 32 kV, 4 milligray dose, 4,800 projections, 6-meter propagation distance. This is the reconstruction using new method, UTI, Unified Tomographic Reconstruction, from the whole lot of projections. And it's virtually indistinguishable from the extract reconstruction in this case. But if we reduce the number of projections to only 480, so effectively reduce the dose to 0.4 milligrays, then interestingly enough, the new method can produce much nicer image compared to extract. It's somehow less noisy. It shows the structure better from exactly the same input data. And I cannot claim that I understand this effect completely, but I think there are two things which contribute to the better quality of the new reconstruction. Firstly is that the new process is completely three-dimensional. So we take into account not just a single slice as our current method does during its reconstruction, but all the adjacent slices as well. So that in principle allows for better noise filtering, which is actually implemented in this new software. So, well, whatever is the reason, the result seems to be encouraging. The second example, where the result is actually not so encouraging, you can say again, this is the extract reconstruction, this is the UTR reconstruction. It may be slightly better, but it's pretty comparable here. But you know why? That's because that scan was collected at 24 milligrays. So even after we select every 10th projection only, the dose here for the lower images is still 2.4 milligrays. So that's not a particularly low dose. And I think, therefore, the results are still comparable for the old and new reconstruction method, right? But I just wanted to include this example because, sorry, this is a different sample, a different energy, by the way, the different dose, and you can see the new method still works, and if anything, slightly better than our current method. And then the final example, where we have very thick sample, it was scanned in a 12-centimeter diameter cylinder, so it doesn't quite fit into the old Hamamatsu detector field of view. So this is the reconstruction from 4,800 projection. The dose was 8 milligray in this case. And this is the reconstruction using the new method from 480 projections, so from 0.8 milligray dose, right? Pretty good, I think. I don't know how much detail you can see at your end. Hopefully, it's not too bad. And at least it should be possible to see that the quality of this new reconstruction is really better than the extract reconstruction from the same data. So again, that looks quite encouraging. It seems like at low dose, the new method really becomes better. Oops, sorry. So here are my conclusions. And I'm not sure if I have to read them aloud, because I pretty much have said all of these things already. So the new method seems to be outperforming the old ones at low doses. That the new method is quite flexible and can incorporate better incorporate any scanning irregularities or different scanning geometries. We are now starting to investigate the extension of that method to cone beam geometry, which is of course relevant to imaging with microfocus X-ray sources. And that's where there is a slight possibility for virtual optical sectioning. Excuse me, I wouldn't bet on that, but it's definitely an interesting thing to investigate. In the worst case scenario, it will just work as normal, or probably again slightly better than the old method. And the software has been developed, tested, and released publicly, available at GitHub. It can work under Windows or Linux, including multi-core PCs or computer clusters. So that's pretty much the end of my talk, and I would like to acknowledge the funding from NHMRC for this work. Thank you very much.
Thank you very much, Tim. And you do have this extraordinary way, but despite the two mathematical slides of explaining things to us mere mortals in a very kind and informative way. So thank you for that. So we're open for questions. So if anybody's got any questions for Tim, please fire away. Yakov.
Hi, Tim.
Hi.
My question is regarding these low dose CTs. So essentially, you compared sort of standard reconstruction approach and a new one.
Yep.
Essentially by reducing the number of projections.
Yep.
Did you compare results when you essentially preserve the number of projections but reduce the total dose?
Not yet, Jakub. No. And maybe another question which you haven't asked yet, but probably we will later or would like to ask, is that I also haven't tried different filters in extract. I know that you implemented various filters for which are designed to reduce the effect of noise, and I haven't tested them yet, right? So I just used the standard reconstruction, the same as I used for the full projection set. I did one more thing which I didn't advertise. I actually slightly filtered the extract reconstruction images to bring them to the same kind of resolution and grayscale level as my UTR images. Mm-hmm. But if anything, it made them better, because without that filtering, they're completely noisy. So I honestly tried to present those extract reconstruction in the best possible way, and I adjusted them to the same scale as the UTR images. So that's really as good as it gets without the thing that you mentioned. I haven't tried the full number of images with reduced number of photons.
Yeah.
And I haven't tried the special filter.
Yeah, because my guess is that FBP is intrinsically limited in terms of if you do not satisfy the prescribed number of projections, it definitely produces low or poor reconstruction compared to say regradient methods, which I guess your UTR method is one of these methods, because you essentially do regradient in the Fourier space. So essentially your sampling in the Fourier space is much better compared to FBP, right?
Yeah. But by the way, I did use grid rec as well in extract.
No. I'm talking about your method, because I guess what you do, you essentially fill all Fourier components by proper regrading of all available projections, and that actually provides all sort of sampling in the Fourier space, proper sampling in the Fourier space, unlike FBP, because in FBP you just have this sort of limited number of sort of planes, and that's why you see all this sort of whatever noise or fringes. It's a known feature of low number reconstruction with FBP. So from my point of view, it's not related mainly to noise in images. It's mostly some bias in FBP reconstruction in the case of low number of projections. So this is why I'm asking if you could do same sort of reconstruction, but preserving the prescribed number of projections.
Right. I can easily test that in the coming days. Yeah.
Because that would be more sort of a fair comparison of these two methods.
Yes. But even that wouldn't be the end, right? Because it would be quite fair to try different filters in FBP, right? If noise still appears to be a problem.
I guess TIE home by itself is quite a good noise reduction filter.
Yeah, that is certainly being used.
Yeah. Okay. Thank you.
Okay. Yeah. This is Sam. Yeah. I don't know. I missed the first part of it because of the URL that doesn't work, and eventually I saw that David sent another URL that works. My question is that would that the new method works any different for low transmission cases, such as if the sample may be large or dense? So in a more conventional method, you need at least 30% to get a reasonable reconstruction. Would that low transmission be works any different or better?
It could be, because if you don't have enough photons, you actually have higher noise, right?
Yeah, that's it.
And if I'm correct that the new method copes with noise better, then it can produce better results from low transmission images. And I would be happy to check that, Sam, with you if you are interested. As I said, all the software is free, so I can happily explain how to use it if necessary, if you have particular images or cases where you think it might be interesting to test.
Yeah, that'll be very interesting. Say particularly for metal, we want to look at a relatively large sample, but they typically get a very low transmission ratios because it's hard to get the high energy photons.
Well, I think that if you have this kind of artifact due to, known artifact due to the very high absorption, these high absorbing areas tend to create this sort of a starring artifacts in the reconstruction. I think that the new method still suffers from the same problem, but yeah, anyway, probably worth checking, because it's very easy to check.
Okay.
I have a question, Tim.
Sure,
that's wonderful method, I think. And I just wondering if whether or not you try with the same number of projection using UTR. For example, for 4,800 projection, is it like there is improvement from the extract TIE home, or?
Not really. It looks pretty similar.
Okay.
Looks pretty similar. When you have all the data or the sampling, the low noise, it seems to be doing as well as extract, only slower. I haven't mentioned that I have worked hard to speed up my reconstruction, but I still cannot compete with extract. And really, kudos to Darren and Jakub and others who made extract as efficient. And now, when I was working with it, I realized how incredibly efficient it is in terms of the speed of the reconstruction, and particularly file I/O. It's just amazing how it can take 15 gigabytes of data and produce a reconstruction in 1 minute. That's just unbelievable.
Yeah. So the benefit you see much better when you use small projection number.
Higher noise, yes, but
yeah, okay.
Of course, what Jakub just said, it remains to be verified. But yeah, you saw the examples that I showed. So at the moment.
Okay, thank you, Tim.
You're welcome.
Just for clarification on that last point, and just I may have missed it, Tim, but on the first set of images that you showed, which I think you used in your paper, am I not right in thinking that your UTR technique at the same number of projections showed significantly better image quality than the old technique?
Yeah, that appears to be the case. Yeah. But what Jakub said, he gave quite legitimate arguments that it is known that the filtered back projection reconstruction, which is implemented in extract, is sensitive to to the insufficient number of projections. It tends to produce artifacts. So if we take the same dose but distribute it over, say, all 4,800 projections, then the outcome may be different. It could be that in that case, the extract and UTR will give the same result. It still doesn't deny the fact that at this lower number of projections, UTR performs apparently better, which I guess is nice because as far as I understand, we are going to collect fewer projections with live patients anyway. So that is potentially a good advantage. Yeah, so lots of things remains to be investigated. Yeah.
Okay. So your intention is over the next year or so, as we gather more information and more images from mastectomies, to keep trying and perfecting this new algorithm?
The very next study that we discussed with Amir already would be to take a set of samples that we analyzed before, maybe a 12 scan set, and reconstruct it both with extract and UTR at low doses, because it currently seems that doing it at high doses doesn't give anything new, but at low doses, and see if indeed we can demonstrate that the new method produces noticeably better results in that case across this whole 12 scan set.
Thanks, Tim. Any last minute questions for Tim?
Not a question, Patrick. Thank you, Tim, for the presentation. And I just wanted to apologize for sending a wrong URL this morning when I sent the reminder. I copied the link from the news section of the Impact website, but it seems the link was not updated. So I resent the link again when you were half of your presentation, but just wanted to confirm that we have recorded this session and it will be uploaded on the Impact website later.
Thank you, Amir. All right, well, I think that's it. Tim, once again, thank you very much for a really interesting talk and again, explaining it in a way that all of us could understand. So that's useful, and we really look forward to seeing how this moves forward over the next year or two. So thank you.
Thank you very much.
Okay. See you, Tim. Bye.
Thank
Bye,
you.
everybody.
Bye.
Bye.